Okay, in this next section, we will talk about roles and the mean value theorem. So we'll start with the mean value theorem first, and just like previous theorems that we talked about, the IVT at the very beginning, and we just finished up with the EVT, which is the extreme value theorem, these are all existence theorems. Okay, and with an existence theorem, you just have to prove that this scenario exists. You do not have to prove what the value is. So for the mean value theorem, abbreviated as MVT, okay, there are some stipulations that must be established first. So we need to let f, our function, be a continuous function on the closed interval. So that's stipulation number 1. So the closed interval is from a to b. So we can have a continuous function from negative infinity to positive infinity, but we're really looking from one endpoint to the other. And then this function must also be differentiable, okay, on the open interval from a to b, because if you close that off, you can't take the derivative at the endpoints. Then what we're saying is there is at least one point c on the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. Okay, so all of this notation should look familiar to you, because really what this is the derivative, which is the slope of the tangent line, needs to be equal to, this is finding the slope, okay? So this is the slope of the secant line. So what we're saying here is really the mean value theorem. If we're proving this, we have to identify the slope of the tangent line, meaning take the derivative of the function given and set that equal to the slope of the secant line, which we would then have to plug in values and get a numerical value here, and then turn around and solve for the value or values of x where this would occur. Okay, so graphically, this is what's happening. We have two different graphs here. So we're given a continuous function, okay, and we close it off from a to b. We're saying we're only looking at this portion of the graph. So what we're looking at here is if we plug in our y value, or a, f of a, and b, f of b, and we find the slope of the secant line by plugging in those numbers. So this is going to be a numerical value because it's a closed interval. What we're saying is there is going to be some value in between a and b, and they call it c, such that the slope of the tangent line will be equal to that. So here, this slope of the tangent line, we use the derivative to find that at that given value. So we're saying that these would be equal to each other, and there's some given x value between these two numbers here where that will occur. This graph just depicts the fact that there's more than one, and it can happen. So here we're saying we have a continuous function. We're closing that off on the interval from a to b. So we find the slope of the secant line, meaning y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And then we set that numerical value equal to the derivative, okay, at this point, and the derivative here. So that's all we're looking at. Okay, that is the scenario for the MVT. So if we had to apply this in a problem, what would we be asked for, and what do we have to say? So there are some specific things that we're looking for when you're answering this question. So it must be answered in a specific format. So here it says, verify the hypothesis of the mean value theorem, and we want to show that they are satisfied on the given interval, and we want to find all values of c, or the x values. Remember, these right here are x values that satisfy the conclusion of the theorem. So we're looking at the mean value theorem. So when we see MVT, or the mean value theorem, we need to think to ourselves, okay, we want to find that the slope of the tangent line is equal to the slope of the secant line. Okay, so here we have a function, and here we have our interval. So first of all, you must state the following. Okay, so up at the very beginning, right here, we stated that the function must be continuous on the closed interval and differentiable on the open interval. So we need to state that. So we're looking here. Now, if we just look at this function like this, we can clearly see that this function is not defined at 0, okay, because you can't have a 0 in the denominator, but we're not asking about 0. So this function is continuous on the closed interval. All right, so you need to think about that. So we must state the following. First of all, in the hypothesis for the mean value theorem, we're going to state condition number 1, f of x, meaning this function, is continuous on the closed interval from 1 to 4. Okay, you have to state that. So we're saying that the function's continuous. Then the second part that we must state is that we can take the derivative of this function. Well, if you look at it, you can take the derivative. Okay, the break, or in this case the vertical asymptote, is at 0. We're looking from 1 to 4. Okay, so then we would just state that f of x is differentiable on, and it's got to be the open interval, sorry, from 1 to 4. I almost wrote from 1 to b, a to b. Okay, so it's not going to be differentiable at the endpoints because we don't have the rest of the function on the other side. So there's the hypothesis. So what's the conclusion? Our conclusion is the actual math involved, okay, by finding the slope of the secant line. So we're going to do that first. So we have our points 1 comma something and 4 comma something. These are x values, right? So in order to find the y value, we're going to plug 1 in here. So this becomes 5 minus 4 over 1, which is 1. So there's a point. Plug in 4. So 4 over 4 is 1. 5 minus 1 is 4. So these are our points. So now we're going to find the slope of the secant line, which is basically y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And that's the same thing as what I wrote at the top of f of b minus f of a. Okay, so here we have 4 minus 1. So it's 4 minus 1 over 4 minus 1. So this becomes 3 over 3, or 1, which is the slope of the secant line. Okay, 1 is my slope of the secant line. So we found the first part, because remember, you have to set the slope of the secant line equal to the slope of the tangent line. Well, the slope of the tangent line is the derivative of the function. So we're going to find the derivative of the function. So what we need to do is rewrite this in friendly form. So f of x is equal to 5 minus 4x to the negative first. So we're going to take the derivative. So the derivative of 5 is 0. The derivative of negative 4x to the negative first becomes 4x to the negative second, which is 4 over x squared. So we want to set, this is the slope, or how we would find the slope of the tangent line. This is the formula because it's the derivative. So we want to set this equal to this. That's the MVT. So we're going to take 4 over x squared and set it equal to 1. Then we'll turn around and solve for this x value, which is essentially the c. They're just using c because it falls in between a and b, just using a different variable. So this is 1 over 1. Cross multiply, so we have 4 is equal to x squared. We're going to solve for x. X is equal to, when you take the square root, you get 2 answers, plus or minus 2. So what we need to make sure of is that when we look at our answers, they fall within the interval. So we're saying that this c value that falls on the interval from a to b could be equal to negative 2 and positive 2. But remember, the interval goes from 1 to 4. So the problem here is that one of these values doesn't work. This doesn't always happen, but in this case it does. We would not include this value here. So you could write your answer as either c is equal to 2, or if you wrote x is equal to 2, those are both acceptable. So what we're saying is, on the graph of this function right here, the slope of the tangent line, meaning the tangent line tangent to the curve, okay, and the slope of the secant line from 1 to 4 will be exactly the same when x is equal to 2. That's what this is saying.